Hello, folks. Welcome to the Defect Chemistry of Ceramics course. So this is already part 4. Up to this point, we have learned only ionic defect structure. Today, we are going to learn electronic defect. What are defects? We learned that defect refers to any deviation from the ideal structure. So in order to understand the electronic defects, we should understand first the ideal electronic structure. Okay? What is the ideal electronic structure? Let's take the metals. We learned from the elementary solid state physics course that the ion cores are distributed in the sea of free electrons. So all these electrons have come from the each ion cores, but they are shared by all these cores. This is metallic bonding. What about the ionic bonding? Okay, here is a very simple story you have to understand first. Here is the neutral magnesium atom. Okay, this neutral magnesium atom consists of the divalent magnesium ion core surrounded by two outmost electrons. Pay attention to these two electrons at the, in the outmost orbital. Suppose that you remove these two electrons away, then you are left with the only ion core, which is the divalent magnesium ion. So I would like you to remember or memorize this cartoon. Okay, this means neutral magnesium atom, and this means magnesium ion. Okay, what about the anion? Neutral oxygen. Let's take the example. Neutral oxygen, consists of just a neutral oxygen atom with empty electron sites at the outmost orbital. This is neutral oxygen. What would happen if filled up these two empty electronic sites with electrons? Then you end up with oxygen ion with a unit of charge of -2. Okay, this is oxygen ion. In ionic bonding crystal, this kind of ion, cations and anions are aligned in alternative way very regularly. So plus ion, minus ion, plus ion, minus ion in this way. So in comparison to the metallic bonding crystals, you can see that electrons are highly localized. Say electrons which used to be with cations come to the anion here. Okay, so electrons are very much localized. So here, empty site around the cation, you see, this is the site for holes. And here, actually, because this is empty, it has no charge at all. So this site is now empty. So emptiness has no charge at all either. So this is called, say, conduction band. So in ideal crystal, all conduction band is empty. So there should be no electrons at all. So this corresponds to the ionic vacancy. Therefore, as far as the electronic defect is concerned, we normally use hole, just empty, to represent emptiness. And effective charge is 0. Okay, this is conduction band. What about these ions, these electrons in the outmost orbital of the oxygen atom? So this is called valence band. Now, valence band is supposed to be filled with electrons with a negative charge. And there, negatively charged electrons are sitting like this. Therefore, it makes neutral electrons. So normally, we represent this ideal state, the hole on in the conduction band, and the electrons on the valence band. So this is the ideal electronic structure as far as the ionic crystal is concerned. So please try to remember these two Kreyper notations. For electrons sitting on the valence side with effective charge 0, holes sitting on the conduction band, okay? This conduction band holes, looks like this, and electrons on valence band here. Now let me show the a typical semiconductor, whose electronic structure is in between. So actually, the outermost electrons of each ion core, is shared by nearest neighbor cations. So in this sense, it is distinguished from the metallic bonding. Okay, so in conclusion, what the ideal electronic structure is? This is the ideal electronic structure. All valence states are filled with electrons, and all conduction band is so say filled with holes, emptiness. That's it. Now then, let's consider what kind of defect may arise. Here we have the ideal electronic structure. Okay, all electrons are sitting on the valence band, and all conduction bands are empty. You see, all conduction bands are empty. As the temperature increases, due to the entropy effect, you see, these electrons on the valence band jumps up to conduction band to fill up the empty side on the conduction band here. So say this makes a free electron, and this effective charge is -1. And this side on the valence band, it used to be filled with electron, but electron now jumped up to conduction band. Therefore, there is left with a vacant side, which is represented by H, hole. And what about the effective charge? Yes, H is the effective charge. Actually, there is just nothing. Therefore, the actual charge is 0. But this original side is supposed to be filled with the -1 negative charge. Therefore, effectively, it is positively charged. So this is called hole and electrons. So this kind of reaction can be written following the chemical reaction. So valence band electrons and the empty side on the conduction band, they are also reacting together to create holes on the valence band and the electron on conduction band. Pay attention to the effective charge. Okay. In defect chemistry, we normally represent this reaction in a bit more simpler way. Just transpose left-hand side, so say reaction side to the right-hand side, to have this kind of combinations. You see, electrons on conduction band less the conduction band side, okay? And the other combination corresponds to the holes on the valence band less the side itself. Okay? So this combination is called, so say, electrons, and this combination holes with effective charge positive. Okay? Actually, this kind of combination of structure element is called building unit. Building unit means a association of a structure elements which satisfy the structure condition. Now have a look at this combination. You take the one conduction band side and now remove it. Therefore, there's no side change at all. Okay, so this combination is called building unit. So actually, strictly speaking, this should be called building unit electrons, and this one building unit holes. But anyhow, let's call it electrons and holes. Okay, and to create this defect, you see, these electrons should jump to the empty conduction band side. Therefore, we have to do work. That work corresponds to the the intrinsic electronic defect formation gives free energy. Well, due to the thermodynamic identity, this Gibbs free energy is nothing but the combination of enthalpy and T times entropy. Okay? But entropy associated with the electronic excitation is negligibly small. Therefore, normally it can be neglected. And then you have only enthalpy term. This enthalpy term is normally called band gap in the solid state physics jargon. Actually, this kind of electronic defect formation reaction looks like the metallic Frankel defect formation reaction. Now have a look. Silver on silver side and empty vacancy side, empty interstitial side. Okay, then that the silver moves to the interstitial side, like the electron jumps to the conduction side. So actually, this electronic defect formation reaction is the analog of cation Frankel defect formation reaction. Okay? Normally, this kind of defect are represented in solid state physics in terms of the band picture. We learned, what the conduction band and what the valence band is, and what are free electrons on the conduction band and the holes on the valence band. Okay. Have a look. Here is the intrinsic electronic excitation reaction. Okay, with the necessary energy of band gap, Eg. Okay? Actually, all bond can be represented in terms of the electronic band. So the uppermost band consists of the valence band and the conduction band. For the case of metallic bond, you have already filled up the valence band, and the extra electrons are partially filling up the conduction band. Okay. What about the ionic cells? If it were just ideal, then all electrons occupy the all valence band up to this point. So this level is called the valence band edge. In terms of energy, we normally represent the E sub V. And then conduction band edge is located above this valence band by as much as, say, band gap energy, Eg. Okay? For the case of the ionic crystal, this band gap is much larger than thermal energy. But for the case of typical semiconductor, okay, then band gap is only on the order of 1 electron volt. So you see, when you create the electronic defect, you have to do work. You have to do work by this much. Okay, and this is simply because of the entropy effect. So therefore, this electronic defect is also the thermodynamic stable effect. As temperature increases, the electronic defect concentration increases. Okay, then how to calculate the equilibrium defect concentrations? Yeah, we can use the defect chemistry logic, which we learned already. Now, due to the internal equilibrium criterion, as temperature goes up, then due to the entropy effect, you have to create electronic defect in this way. Now, you have to do work by as much as the intrinsic electronic defect formation energy. Okay? So here, free electron is here. Okay? Now, holes are here. Now you can make the interrelationship between the bond picture, electrons and holes, and those in band picture. By applying mass action law here to this chemical reaction like electronic defect formation reaction, you can simply write the product of these two, so say, reaction product, electron concentration and hole concentration. Normally in solid state physics, electronic concentration is represented by N and the hole concentration by P. Okay? So MP product should be constant. This constant Ki is called intrinsic electronic excitation equilibrium constant. So for a single component system like a silicon or germanium or whatever, in such a case, there is no composition variable. Therefore, this equilibrium defect formation constant should be a function of thermodynamic variables, which are temperature and the pressure. Okay? Then this can be factored into the temperature independent term and the temperature dependent term. Temperature dependent term, consists of the defect formation energy. In this case, actually band gap. Okay? Now, as you see here, temperature increases, electronic defect concentration increases exponentially. Okay? And now, if your system is totally absolutely pure and the composition is fixed, then due to the charge neutrality condition, electron concentration should be equal to that of the whole concentration. Then N equal P, okay? Probably, N equal P relationship, you learned it from the solid state physics course. Okay, up to now, we learned the electronic defect of the intrinsic origin. By intrinsic origin, say defects are formed only due to the entropic effect. Okay? There are also the electronic defect of the extrinsic origin. You know what extrinsic origin means. Okay? In the when we learned ionic defect structure, you see when we plotted ionic defect concentration against reciprocal temperature, normally high temperature part is called, say, intrinsic regime, and the low temperature part, which is controlled by the impurities. So that region used to be called extrinsic origin, extrinsic regime. Okay, so impurity induced electronic defect. Okay, that is the electronic defect of extrinsic origin. Typically, there are two things: donors and acceptors. Okay. Now, let's study what donors are. Suppose that we have the pure silicon. Silicon, is covalently bonded with the other neighboring silicon by sharing, 4 electrons with each other. So to fill up the, 8 electron site at the on the outmost, orbital. So in terms of the defect, you see, silicon is now sitting on the silicon side. And the silicon side, if the crystal is, ideal, then silicon side should be the place where the positive charge of unit 4 are located, right? Here. And then tetravalent silicon is sitting upon there. Therefore, its effective charge is 0. So this is pure silicon. Now, suppose that you are substituting this silicon with pentavalent phosphorus atom. Okay? This phosphorus atom has the 5 electrons on the outmost orbital. So now suppose that you put the, one pentavalent phosphorus atom on silicon side in this way. Now this phosphorus, atom donate its own 4 electrons to make bond, but still it has 1 more electrons here. So actually, this part corresponds to the neutral silicon, because it makes, so to say, tetravalent phosphorus ion on silicon side, tetravalent silicon side. Therefore, its effective charge is 0. But remember, still there remains 1 electron here. Now, temperature goes up. Then, of course, there is a certain, certain degree of attractive interaction between this ion core and this electron. But temperature goes up, then entropy, wants to make everything disordered. So this electron is detached from its host, say phosphorus, to go away. to the conduction band. So you see this phosphorus ion donates, say, 1 electron to the conduction band. So in terms of the actual charge, this state can be written in this way. You see, pentavalent phosphorus ion is now sitting on the tetravalent silicon side. Therefore, its effective charge is +1. So that's why it has the 1 dot. Okay? Why does it have 1 dot? Because this phosphorus ion gave up the last 5th electron, okay, to the conduction band. Say donated electrons to conduction band. So that's why this kind of impurities is called donors. So this reaction can be written in this way in terms of the defect chemistry jargon. Now I have the, so to say, tetravalent phosphorus ion on silicon side. Okay, here this thing, and then conduction band has remained empty. Okay, now 1 electron jumps up to the conduction side to make 1 electron here. By doing that, this phosphorus ion becomes pentavalent. Okay, what about the effective charges? Now this guy becomes, this is neutral one, but pentavalent phosphorus ion sitting on the tetravalent silicon side, so makes the effectively positively charged by 1 unit. And then combination of these two things makes the building unit electrons in the conduction band. And this attractive energy is called, so say, ionization energy. Okay? Because this impurity donates electrons to the conduction band, therefore it is called electron donors. As a consequence, this material, the phosphorus doped silicon, makes an n-type semiconductor because electricity charges are transported by these free electrons. Solid state physics people likes to represent these kind of things in terms of band. It's quite simple. Okay, here is the conduction band. Now our neutral phosphorus, namely tetravalent phosphorus ion on silicon side. So effectively it's neutral. But don't forget, now it contains these electrons. So by detaching 1 electrons from the tetravalent phosphorus to conduction band, you have to supply the energy as much as this. If this electron donation energy, so to say, ionization energy, it depends on the size of this ionization energy depends on the impurities. If this energy is pretty large, in such a case, those impurities are called deep donors. And particularly when this energy is small, so this energy level close to the conduction band edge, then it is called shallow donors. Quite simple, isn't it? Well, how about the equilibrium concentration? It's again simple. Here is the defect formation reaction. We call it ionization reaction or internal equilibrium. Okay, so this is the donating electron donation reaction. Okay, and you need electron. You need the energy of ED to detach electron from tetravalent phosphorus ion to a pentavalent. Simply by applying the mass action law, you can just write in this way. Say product of this product, concentration of product concentrations divided by reactant concentration makes a constant, namely ionization reaction equilibrium constant for the case of donor. Okay? Well, like the intrinsic electronic excitation, again, this equilibrium constant can be factored into 2 terms. One is, say, temperature independent term, so say pre-exponential term, and then temperature dependent term. Now you can see the Boltzmann factor here involving the ionization energy. Okay? And one thing you have to remember, in any case, it doesn't matter how much ionized or, it doesn't matter. Always, mass should be conserved. Therefore, neutral phosphorus ion and pentavalent phosphorus ion. So their sum should be constant. Actually, this is the amount you originally doped your crystal. Okay, okay, that's it. Then what about the acceptors? Let me again go back to pure silicon. Okay, let me remind you that pure silicon, consists of this structure element, silicon on silicon side, silicon side. Therefore, its effective charge is 0. Okay, so every lattice side is filled with this structure element, ideal silicon. Now, suppose that you are substituting this silicon with trivalent aluminum. Okay? Aluminum tends to be trivalent because it has the 3 electrons on the outmost orbital. Okay? What would happen then? Have a look. Aluminum has the 3 electrons outside. Okay, now this aluminum on the silicon side donates electrons to make this band, and the second electron here, third electron here. Oh, that's it. Aluminum has no more electrons to, to donate to make the, the band. So it has the empty electron side. What is this? This is nothing but the hole on the valence band, because this bond, corresponds to the valence band. So this trivalent aluminum, keeps the one hole together with itself. So actually, this kind of combination, okay? Trivalent aluminum on tetravalent silicon side, okay, together with these holes. So this makes this aluminum on silicon side neutral, effectively. Okay. Okay. As temperature goes up, what would happen? Yes, these holes can be freed because of the entropic, disordering effect. So now, these holes moves to the other, valence band side. In this case, the electrons which used to be here moved to this side. Oh, yeah, here, this side. Again, in this case, you need to do some work to detach these holes to move to the, this another valence band side. Let's call it, say, EA. So this reaction can be written in the same way as the chemical reaction. You see, I have this complex, and I have the electrons on the valence side. Now, you can take up this electron to fill up this empty side, okay? And then you release these holes to the valence band. Now, move the, this structure element to the other side to end up with the free holes. Okay? So in defect chemistry jargon, you can simply write this, so say hole donation reaction in this way. Now neutral silicon, neutral aluminum on silicon side. You know what it is, right? This stuff. Now it gives up holes to the another valence band side, and then it itself becomes trivalent. Therefore, its effective charge is -1. All right. So this kind of the lower valent impurities works as the, so say, hole donors to valence band. In previous case, we learned electron donors, but in this case, actually hole donors. But we can say, on the other way around, by donating holes, you have to pick up taking the electrons from valence side, right? Which used to be on this side. So in this sense, this kind of impurity is called electron acceptors, namely taking electrons from the valence side, valence band. So when you have the this kind of electronic defect, okay, then temperature goes up. These empty sites can move around, which makes the your semiconductor p-type. So this is normally called p-type semiconductor. In terms of the band picture, it is quite opposite to the electron donor case. Now neutral aluminum, okay? Silicon side here, this one. Then in order to accept these electrons from the conduction band edge to this side, you need to apply the energy of EA, so say hole binding energy, or for this electron to jump to this energy, to this level, then you need energy, right? Okay. If this energy is much bigger, so that this level close to the center, then this kind of impurity is called the deep acceptors. And when this energy level close to this valence band edge, those impurities called shallow acceptors. So quite simple, right? Okay, then how could we calculate the, so say, thermodynamic equilibrium concentration of, so say, ionized acceptors? Yes. Yeah, we can write down ionization reaction here. Okay. Neutral aluminum on silicon side gives up one hole and makes, say, trivalent aluminum on silicon side. So you can simply apply the mass action law to get this expression, namely concentration product of these two products divided by, reactant concentration. Again, this equilibrium constant is called the ionization equilibrium constant. In this case, for the case of acceptor. So I put A here. So like the previous case, it can be factored into, say, pre-exponential factor and then Boltzmann factor involving the ionization energy. Again, don't forget how much, it doesn't matter how much ionized whatsoever, always some of this ionized impurity and the neutral impurity, their sum should remain constant, which is the, so to say, doping level. Okay? Now we are on the stage to understand a bit more complicated cases. Yes. Up to now, you understood, you learned intrinsic electronic defect, electrons and holes, and then donors and acceptors. Okay. Okay, now let's go back to the point defects in ionic crystal MO. What kind of defect there were? We learned, say, metal vacancy. This is the divalent oxide, okay? Okay, so missing cation. Therefore, its effective charge is -2. And interstitial metal, which is effectively positively charged by unit 2, okay? And missing oxygen ion, therefore its effective charge is +2. Now, oxygen interstitial, okay? Oxygen interstitial, you see, it used to have the 2 electrons with it. So now, this whole entity goes into the interstitial side. Therefore, its effective charge is, double prime, okay? Now, have a look. What is the regular structure element, cation? So M on M side with effective charge, 0 effective charge. This means divalent cation is sitting on the divalent cation side. Okay? I draw a cartoon here. This corresponds to the neutral metal ion on metal side. Pay attention to this empty two holes. Okay? Because this metal atom used to have the two electrons here. To make this crystal, this metal atom gave up these two electrons to the nearby oxide ions to make, oxygen anions. What about the neutral oxygen anion? Okay, oxygen on oxygen side. This means, say, oxygen ion with the charge -2 is sitting on the oxygen side, whose charge state should be 2-. Here, this is the neutral oxygen on oxygen side. Now have a look. What about this entity? This corresponds to the neutral, M ion on M side. Now, if you include these two electrons, which are combined with this nearby N ion, okay, then this whole entity makes neutral metal atom, right? Because these electrons used to be the missing electrons nearby, near this cation side. Okay, this is neutral M. What about neutral oxygen? Yes, here it is. Without these two electrons, okay, this makes the neutral oxygen. Okay, now I think you can easily understand, what neutral M is, what is the neutral metal atom is, or regular structure element, and so on. Now suppose that you have you take out this ion. Okay. Now you see you have the regular structure element on M side, M ion on M side. Okay. Now you are taking out divalent metal ion. Then what is left? Yes. So missing N ion, which has the effective charge of the -2 unit. What would happen if you remove the metal atom instead of metal ion? This means you are taking out this entity as a whole together with these two electrons. Okay. Now you are taking out metal atom from the ideal crystal. Then you took out, because you took out the neutral M, the remaining metal side, the missing metal side, actually each side, it makes the, this ionic defect with effective charge of -2. And then you took out these two electrons together. Therefore, you left behind two holes. So what's that? This makes the neutral metal vacancy. Okay? This neutral metal vacancy, don't forget, this neutral metal vacancy has two empty electronic sites and nearby, valence band. Then what would happen then? Okay, now this neutral metal vacancy gives up one holes. So it's the first ionization. Then remaining ionic defect has the effective charge of -1. Yes, that's why it has the single prime. Okay, still there remains one more holes. Okay, now this guy gives up the last hole to make the, so say, fully ionized metal vacancies. This kind of reaction is called first ionization reaction, and this second ionization reaction. Of course, you see, you have to do work, or you have to apply energy to detach one hole and the next holes in this way. Therefore, neutral metal vacancy works as the acceptors, right? Because, they are working as hole donors. Don't forget, neutral metal vacancy corresponds to the missing neutral metal atom, this entity. Okay. Okay. Now let's pay attention to the anionic sublattice. This is anion. If you remove this anion, or 2 minus, then you end up with the missing anion with the effective charge of +2, because your crystal is now missing the divalent anion, therefore effectively positively charged. Now suppose that you remove this neutral oxygen instead. This means you are leaving behind these 2 electrons on the valence band. Okay? Actually, these 2 electrons used to be occupied, or under the reign of this anion. Okay, this oxygen. If you remove the neutral oxygen atom from the ideal crystal, then you're left with neutral oxygen vacancy. This corresponds to the actually divalent oxygen vacancy. Oh, this is a typographic error. It should be 2 dot. Yes, okay, 2 dot. Because you are removing this one first and left behind 2 electrons. Okay? Therefore, in total, it makes neutral oxygen vacancies. It has 2 electrons with no owner. Okay? Now, this neutral oxygen vacancies gives up 1 electron. And then this one, again, donating the last electron. So this is called the first ionization, and this is second ionization. Again, you need to supply the energy to detach electrons from this entity. This is quite amusing, isn't it? You see, so therefore, neutral oxygen vacancies, which corresponds to this one, you see, corresponds to this entity without this ion core. Okay? So oxygen vacancies are called donors because they are donating oxygens. What about, let's suppose that you introduce one neutral atom, okay, at the interstitial site. Then this metal atom, you see, has the 2 electrons, at in its own outmost, orbital, or 2 electrons. Okay, so it is still electrically neutral because you are you have the neutral metal atom on the neutral interstitial site. This means metal ion, you see, is still keeping 2 electrons to make neutral. Now you can easily expect what would happen then. Okay, 1 electron is donated to conduction band, and the second one also. But this works as donors. Okay, now what about the neutral oxygen inside? Okay, suppose that you put into your crystal at the interstitial site an oxygen atom. This oxygen is always hungry for electrons. So this guy wants to pick up 2 electrons from the valence band in the crystal. So by picking up 2 electrons, okay, so it becomes negatively charged oxygen ion, and then the previous electronic site, they remain 2 vacant electronic sites, which are holes. So neutral oxygen ion works as the hole donors. In other words, acceptors. I think you can understand what's going on, by considering just this picture. Okay, here metal ion, metal atom, oxygen ion and oxygen. Oxygen ion and the oxygen atom, and so on. Okay. So let me summarize what you learned up to this point. In bond picture, this is ideal crystal. Have a look. Ideal crystal. These electrons came from this metal atom. Therefore, the remaining core becomes divalent cation. Okay? And including these two electrons, this makes neutral oxygen. Okay? This is ideal crystal. So this is the valence electrons sitting on valence band. Now around the metal ion, you have empty electron site, which makes valence convection band. Okay. Now, if you take out this metal ion, okay, then you have the metal vacancy with effective charge of -2. You understand, right? If you take out this whole thing, oxygen ion, then you end up with this kind of things, right? Therefore, effective charge is +2 because this site is now missing 2 electrons. Okay? Now you understand fully ionized metal vacancy and oxygen vacancy. Now, suppose that you are taking out, not only this ion core, but also with these 2 electrons, this whole entity. Okay, then this makes neutral metal vacancy. What would happen then? These holes in the valence band, okay, move around by accepting electrons from the valence band. So this works as the acceptors, right? Okay, if this guy takes 1 electron, then it's singly ionized. The opposite picture is here, oxygen vacancies. If you take out only neutral oxygen, then this makes neutral oxygen vacancy because there still remain 2 electrons with negative charges. Then it's easy for you to understand why this works as donors. Okay, 1 electron goes to the jump to the conduction band, and now the second one also. So that's why this works as donors. Okay? And the interstitial case, again, you can figure out by using this kind of pictures. Just one example. Neutral metal interstitial. Okay, this means interstitial metal ion together with the 2 electrons. Therefore, it works as the donors. Oxygen interstitial, you see, 2 empty sites. Well, and so on. In terms of band, it's like this. Here is conduction band and the valence band. Let me just point out the conclusion. Neutral vacancy, oxygen vacancy, located here, just beneath the conduction band. Then first ionization needs energy as much as this. And then second ionization, okay? Oxygen vacancies are working as donors. Here, oxygen vacancies, neutral vacancies. Metal interstitial, yes. First ionization, second ionization, yes. Also works as the donors. Here, these are works as donors. And what about the metal vacancy? Neutral metal vacancy. Now, it accepts 1 electron from the valence band to make singly ionized. This must be 1 prime. Sorry for this typography error. And then by taking the second electron, it becomes, doubly ionized metal vacancy. So metal vacancy works as the acceptors. What about oxygen interstitial? Yes, they are also working as the acceptors, electron acceptors from valence band. There is some kind of, the common feature. Donors, metal interstitials, and the neutral oxygen vacancies, right? If you have the more and more metal interstitial, then you have more and more metals, right? So your composition of the composition of your crystal becomes metal excess. And by introducing more and more oxygen vacancies, you end up with the oxygen deficient crystals. Metal excess means oxygen deficit, right? Oh, these guys, yes, metal excess or oxygen deficit. These guys works always donors. And the opposite case corresponds to the metal deficit metal deficit and the oxygen excess case. See, metal deficit, I'm sorry, and the oxygen excess. So don't forget this fact. Always metal excess, because metal is all electron donors, okay? Therefore, metal excess makes your system becomes N-type. And the metal deficit always tends to make your system P-type, because metal vacancy, tends to pick up the electrons from valence band to make the holes in the valence band, okay? Likewise, for the case of the oxygen vacancy and in the interstitial. Yes, so this is the association of the intrinsic ionic defect and electronic defect. That is very important, this fact, okay? This is the key of controlling the electrical behavior of your system crystal. By controlling this ionic defect state, you can make your crystal, either N-type or P-type or insulator, if you like. Okay? Then what about the impurities? Yes, exactly same as the case of the silicon. If you introduce the higher valent impurities, then it tends to be a donors, like phosphorus ion on silicon side. Let me take the aluminum on magnesium side. Magnesium side means divalent, magnesium, ion is sitting there. Now you're replacing trivalent aluminum, okay, for the magnesium ion. Then its effective charge is, so say +1, right? So in terms of the actual charge, you have you see trivalent aluminum sitting on divalent magnesium side. Okay, what would happen if you, if you keep this electron within itself to make the aluminum itself behave as if it were divalent? Then effective charge is just 0, right? Because divalent aluminum sitting on Mg side, but this aluminum has one more electron. I don't like to keep it. Then it donates electrons. By doing that, aluminum itself make the trivalent aluminum ion on Mg side. Okay? So therefore, higher valent impurities always tends to make donors. What about lower valent? Yes, opposite case is true. For the case of silicon, I took the aluminum as the example for acceptors, right? Okay, let me take a lithium on magnesium side. Lithium is singly ionized. It has only one electron, on the outermost orbital. Then, to fill up the entire bond, it has to donate 2 electrons, but it has only 1. Therefore, it should have the one empty side around itself, okay? Like this. So this means singly ionized ion on magnesium side. But what about the lithium itself, which keeps the hole nearby? Then by releasing holes to the valence band, then it turns to the fully ionized this state. Therefore, lower valent impurities tends to act as the acceptors. Everything's clear to you? Yes. That's all for today. So thank you for your attention, and I hope you have enjoyed this lecture. Okay, bye-bye until next lecture.